Okay, so looking at the 380 here, so we're going to go through some exercise. I think I'll try to emphasize a little bit on the MNS again, because we didn't have much time to go over this modified mode theory at the end of the last lecture there. Okay, yeah. Okay, so. So modified mode theory, if you recall that, this is basically in tensile stress dominant situation. For uneven material, brittle material. And failure is due to tensile stress only. So you got to be clear that for the modified mode, as we're going to see, why is modifying? It's based on the experimental observation. Under this tensile stress dominant, so basically, what could be categorized as a tensile stress dominant, right? And then failure is due to tensile stress only. Okay, yeah. Tensile stress only or tensile stress dominant basically means, this is the scenario you're looking at, and only exists in this case, right? There are three cases, only in this case, and also when the absolute value of the sigma A is greater than the absolute value of the sigma B. So this is basically means the tensile stress dominant, right? Tensile stress dominant, and when this is the case at here, then we only consider tensile stress only for the failure, right? For the failure here. So that's why in the handout, if you look at your handouts there, okay, if you look at the handout, and here is your sigma A equal to sigma B 45-degree line. Here is sigma A, here is sigma B. So in the first quadrant, there's no change, right? There's no change compared to the other theories. And then if you plot this one here, which is a sigma A equal to negative sigma B, right? So that basically means absolute value, these two are the same. And above this line over here, right? Over here, this is basically tensile stress dominant area. So this area is tensile stress dominant area. Then according to that theory, then we just recycle this tensile stress, okay, SUT, so no change, right? Just keep going at it here. Okay. Now within the area beneath that line, this is not tensile stress dominant area anymore. So that basically you follow the steps connecting with SUC. Okay. Let's use green color. Okay. And then finally, like this. So this is how the modified mode theory, okay, are connected, okay, to describe the boundaries of the failure, right? Boundaries of failure. So tensile stress dominant, just like the sigma A greater than sigma B. So over this area, okay, over this area here, let's use green color. It's the area less than sigma B, right? That's this area. Okay. Now, in terms of the line equation, right? If you look at this line equation here, that's basically what determining this safety factors, right? Safety factors here, and this is the only information you need actually in terms of the whole boundaries, because the other boundaries are just straight lines, right? The other boundaries are very simple straight lines, and this is only one straight line that's a little bit different. And for this green color, the straight line, and if you look at your handout, okay, and this straight line here is this equation. Okay, so that green color, this is that equation in here. Okay, that's that equation. So technically, you see, if I wanted to calculate the safety factor based on a certain state of stress or based on a certain stress element, there are how many cases? There are 1, 2, 3, basically like 4 different cases, right? So it could fall into any one of the area at here, okay? Any one of the areas. Then when it comes to the calculation of the safety factor, and you can still follow that basically case 1, case 2, case 3. The case 1 is the same as the other, always the same. Sigma A greater than sigma B and greater than 0. That's this area here. Okay, that's this area. So calculating the safety factor basically is the comparison between SUT and a sigma A, right? So that's the SUT and sigma A. So N equal to SUT over sigma A. Right. And then within this case 2, right? Case 2 is this whole area is case 2. Case 2 is, okay, this is the whole area for case 2 at here. Okay. So within this case 2, you have 2 different situations, right? 2 different situations. One is tensile dominant, and the other is the tensile not dominant. Okay, and not tensile dominant. So you can see, okay, for tensile dominant, it's this one, right? If tensile dominant, which is this part, as you can see, calculating safety factor is the same as calculating safety factor in case 1, which is basically comparing the SUT with sigma A, right? Sigma A here. So your N is still SUT over sigma A. But if this falls into the not the tensile dominant case, right, then we're going to use in this green color now in this area. So we're going to use this green line here as a boundary. So your calculation safety factor will be simply just the 1 over this whole thing. Okay, this whole thing, that will be your safety factor. So 1 over that whole chunk there. So case 2, we essentially have 2 different possibilities for calculating this safety factor. And then last case, when you're 0 greater than 0, when this is a third case, and your N just equal to negative SUC over sigma B, right? So just comparing this SUC with sigma B now. And that's how you can interpret the handouts, right? How you can interpret the handout, how to use the appropriate formula for calculating the safety factors. Okay, yeah. So you should also, this, depends on the question. You probably will use one or two or all of them to compare or to just calculate one. Either way, you need to know which formula that you should use, right, in order to find the right safety factor. So this table here, okay, is the right place for finding the safety factor given a certain state of stress or stress element. Okay, so we'll look at the examples here. Okay, a couple examples to calculate safety factors. Any questions so far? Okay. Let's look at an example. So this example here, you have a bar. The bar is attached to a void here. Then we subject the bar to a torque, T. Nothing else but the torque. Suppose it has a diameter D, and since we're dealing with brittle material, so let's consider this is a bar made of cast iron, so that's brittle material, and ASTM30 cast iron. And if you look at your appendix in the textbook, you'll find that its SUT is 31 KSI and SUC is 109 KSI. Assuming that the diameter is 0.95 inch. Okay. So here's a question. Okay. This time let's use BCM theory. Okay, use the BCM theory to find a torque T such that the safety factor equal to 1. So basically, under what torque T, and then they end up with a safety factor equal to 1. Okay. It's a typical static failure analysis question, and of course, PCM it's determined, but you need to basically for this particular question, then you need to determine where the critical location is, right? And what would be the state of stress, or the element, the element of the element of the state of stress. Then you can find out, how to use the BCM, right? Yeah. Now this is a simple loading. There's only one torque, so the critical location must be where? Must be around the edge of the shaft, right? Yeah. So you can literally take any point around the edge of the shaft, and that will be your critical point. Okay. Yeah. And if you take any stress element, you end up with basically pure shear, right? You have a pure shear situation right here, and it's a plane state of stress. It's pure shear, and the shear stress equal to TR over J. So T times half diameter, and J is pi d4 over 32. It's a polar moment area. We don't know what a T is yet, so that's simplified. We'll simplify to be 5.9 times T. Yeah.
How do you know the physical location was at the end of the shaft and all?
Because the torque will cause a shear stress, right?
Yeah.
And shear stress is maximum. You look at the formula here. Is maximum at the edge, which is where the radius is the largest.
Okay.
Right. Yeah. So if you take a stress element here, and you'll see the stress pointing that way. If you take it here, right? So that's how the stress flows around the edge. Yeah.
Oh, so it doesn't matter on which value of x it is.
Really doesn't matter, right? You take a stress element here, you know, it really depends on within which coordinate system we're looking at, right? Everywhere you will see basically it's a plane state of stress. So everywhere you will see, if you look at this, maybe it's this like this, right? You'll see something like this. Okay? Yeah. So when you have a stress element like that, so for example, if I take it from here, I probably will see something like that, right? If I take a stress element like that, then the mole circle will be a circle which for pure shear, which is a circle around the center of the origin. And here's your tau, here's your sigma A, here's your negative sigma B, here's your sigma B, right? Okay. So apparently you see your sigma A is equal to tau, and sigma B equal to negative tau, right? So you have the tau calculated, which is 5.9 T. Okay. That's your sigma A, sigma B. Okay. Once you find your sigma A, sigma B, then it's time to use the BCM. You look at the BCM, and here, where's BCM? BCM is this second column here. So, and then we have to identify what kind of case we're in now, right? In this case here, you see this must be greater than 0, and this must be less than 0, right? Yeah. So you're looking at is the case number 2, okay? And the BCM for case number 2, your safety factor is this one here. So that naturally you can calculate the safety factor by plugging that formula. We have 5.9 T here, 5.9 T here, negative, and N in this case we want it to be 1, right? We want it to be 1 for the N here. So the only variable left is just the torque now. So you can reversely calculate the torque, and then the torque calculated, okay, you can try yourself. Well, let me just so 1 equal to 5.9 T over SUT, so 31 KSI, so that's, let's say, 10 to the power 3 PSI, and then here is negative 5.9 T over 109 times 10 to the power 3 PSI. Solve for the T, and you get 4,900 pound force inch. Okay. Why the multiply 10 to the power 3? This is just converting to a standard unit. So the results you get for the T will also in a standard unit, which is pound force inch, right? So in this question, it actually means your selection of your application of the T should be less than this number in order to maintain your safety factor to be greater than 1. Okay. So that's one example using BCM. That's a simple example. So let's try a couple more examples here. Any questions so far? Okay, good. So let's take the second example. In this example, we're going to forget about the actual loading condition. So we'll just list the some of the numbers here by looking at how can we pick the formula for calculating the safety factor. Okay, so this side, okay, so sigma x is this, and sigma y is this. Okay. I don't know how they end up with this, but it's just assuming under certain loading condition, right? You end up with a sigma x equal to this much. The second scenario is a little bit different. Okay, let's look at these two conditions. So we have this one, and then the second state of stress, which is this. And we're going to actually use all three theories, okay, to calculate safety factors. Okay, all three of them. Now, before we calculate the safety factors using all three of them, okay, so I want you also to do a quick answer here. Three theories. Which theory is the most conservative theory? Which one is the most conservative theory? Red. But what is red? Huh? The Coulomb-Moore, or the Brittle Coulomb-Moore, right? Yes. Okay. Yeah. And in a textbook, you have experimental results. Okay. The experimental results actually shows the modified modes theory, which is this blue color. So this one here is the most accurate one. Okay. So understand what is the most conservative and what is the most accurate among the three theories. Just like for the ductile material, there's distortion energy, and then there's another maximum shear stress theory, right? Yeah. And there's also similar question there, right? Okay, let's come back to this two cases that are here. Since we're going to use the formula, so either we need to calculate sigma A, sigma B, right, before we can use the formula sheet. So here's the formula for calculating the two principal normal stress based on the state of stress. And in this case, we get a sigma A equal to sigma X and a sigma B equal to sigma Y, because there are only two normal stress in place. So that gives us this 20, and this is 6 KSI. And this one here, you do the similar calculation. Sigma A, you will get 4 KSI, and sigma B, negative 16 KSI. Alright, okay, so this one falls into this kind of case, right? So case number 1, so that's greater than sigma B greater than 0. And this one falls into this general second case. So I should just get rid of the equal sign, because we know the value. Alright, now you can look at the handouts now. Okay, so let's say if I'm going to use MNS theory for the safety factor in the question 1 part, in this part of the question, and you look at that basically here, and right, so it's this formula here, right? MNS. So actually, as a matter of fact, all three of them has the same formula, right? And that's basically what the diagram, also the same information we get from the diagram there. Okay. So all of them is the same MNS and BCM and MM. Okay, all three of them will have the same formula. And SUT is 31 KSI, sigma is 20, so approximately 1.55. That's your safety factor. And this side will make a difference now. Okay, for this side, because this is sigma A greater than 0 greater than sigma B. If I look at the second row here, which is the second case, and you'll see the formulas are apparently different, right? Apparently different. Especially for the last one, MM here. And even on this case 2, remember they separate into 2 different cases, right? Yeah, sorry, I'm not sure why the printing is slightly shifted above. So let's look at this MNS at here. Okay, MNS. So MNS calling for getting a minimum between this calculation and that calculation. So I guess we need to calculate both and then find the minimum value. Okay. So let's calculate SUT over sigma A, which is 31 over 4, so 7.75. And then let's calculate negative SUC over sigma B. Okay, so 109 over 16. Okay. So that's 6.81. And then your safety factor is the minimum between these two. Apparently, it's the 6.81, right? So that's your safety factor in this case. And then BCM. Okay, so BCM, it's simple, just one formula. Okay, it's very much the same as the previous question. So it's 1 over sigma A over SUT minus sigma B over SUC. Okay. So plugging sigma A, sigma B, SUT, as you see, it's approximately 3.9. That's your BCM. Yeah, remember BCM is the most conservative, right? So bear that in mind, and let's see if the BCM actually end up the minimum number here. And the last one, let's use MM theory. So for MM theory, if you look at the case study here, so then you have to decide which one of the case we're looking at. Or in other words, it's basically whether it's a tensile stress dominant or it's not tensile stress dominant, right? And that's basically based on the comparison between the sigma B value and sigma A value. Okay? Yeah. So sigma B at here is negative 16. Sigma A here is 4. So this one give me a 4 at here. So that's greater than 1. So which means sigma B is greater than sigma A, right? So that's not tensile stress dominance. Tensile stress dominance meaning the sigma A absolute sigma A value is greater than the absolute value of sigma B value. So then you choose the second formula here, right, for calculating this safety factor. So that N at here is equal to 1 over, you can rewrite this whole chunk of formula here. And that gives me 4.2 roughly. So the number calculated conforms with our expectations. BCM is slightly less than the other two, okay? And MM is the most close one. MS is actually the most inaccurate value, right? Yeah, which makes sense because if you look at the diagram, so because it falls into somewhere probably here, right? The state of stress falls in somewhere here. So when you draw, if you draw lines out, you can see there's a whole bunch of empty areas, right? Yeah, for the MM theory. Okay. So this is how you can make use of that table, all right, to find safety factors. Let's look at one more example. Basically, this example it's nothing new. It's actually an example that we did when we are learning the ductile material. Okay. So if you recall that. You have a, let's see, in this case we have a, remember you have a bar right here, and then there's a arm, okay, and a force applied at the end of the arm, okay. Yeah. So here's a D, here's L. Here's the length of the arm A. Now in this one here, so I'm not going to change anything at all in terms of dimension, and also the force we're going to keep it the same as 1,000 pound force. Okay. The only thing we're going to change is we're going to change this this whole thing into a different material. So this rod that is here, we're going to change to, let's say, cast iron or some other different type of material. So let's say for SUT, so taking 52.5 KSI, and SUC is 164 KSI. So here is brittle material now, okay? Okay, everything else is kept the same. Now, if this is the case, and then we want to do the similar analysis, what will be the critical location, and what will be the safety factor at that critical location? Okay. If you recall, in the ductile material section, we basically picked two different locations. One is at this location, and the other is at this neutral axis location, B location. Because we understand that the A location has a maximum normal stress due to the bending moment, and B location has the maximum shear stress due to the shear force, right? In ductile material, that results, it turned out A is more critical than B, right? So that's the conclusion we have made, because the bending moment, the normal stress caused by the bending moment tends to be more critical situation than the shear stress caused by the shear force. Okay, yeah. So without basically going through all the details again, if you recall, at the point A, okay, at point A, there are two different stress. There's a normal stress caused by the bending moment, and then there's also a shear stress caused by the torque. So if you recall, when I go through the exercise for ductile material, I actually did really detailed steps, right? By drawing the stress element and drawing the stress element in the right direction, according to the right direction of the loading, and also draw the mole circle, things like that, and you calculate, right? But when it comes to the calculation of safety factors, all they need is just the value sigma A, sigma B here, right? Which is based on the state of stress. So the accuracy in terms of sketch the stress element doesn't really matter in terms of calculation of the safety factor. Okay? Yeah. So here's sigma x is tau xy, and m equal to f times L, and the t equal to f times A. So, and all of the parameters and on the I here and G, So you will be able to calculate sigma x, sigma y like what we did in the previous lecture. So then you can calculate sigma A and B, which is according to this state of stress that are here. Okay? And the formula, of course, is this formula. Okay? It's this formula here, right? Yeah. Okay, so for this case, we got 24144 negative 6034 psi. And this is exactly a case like this, right? Case number 2. Okay. So let's try the MM theory. Okay, that one is probably the most tricky part, the MM theory here. So in this case, for MM theory, the first step, you can compare the ratio between sigma A and sigma B. Right? Compare this ratio. This is absolutely much more than the absolute value of sigma B, so the ratio will be greater. The ratio here is greater than 1, right? Greater than 1. So if the ratio is greater than 1, and this falls into that so-called tensile dominant. Okay, the tensile dominant situation. And if it's tensile dominant situation, we use n equal to SUT over sigma A for the calculation safety factor. So n equal to SUT over sigma A, which is 2.2. Okay. That doesn't matter. You use comparison, right? Yeah. but you just have to know which one is bigger than the other one. Tensile dominant meaning absolute sigma of A is greater than sigma B. Yeah. Does that make sense? Yeah. Okay. I want you to try BCM and what's the other one? The MNS, right? So you can try these two, okay, and what the safety factors are. And I also want you to try point B, right? At the point B, you don't have to calculate this all. The stress is already calculated from previous lecture. So at the point B, you have basically two shear stresses only. It's a pure shear at the stress at the point B, and what will be the safety factor? Okay. Good. So try it out, see, and then compare with the values in the lecture notes. Okay, and see if you get the same answer. Good. Okay. So. Let's move on to a new topic now, okay? Yeah. The next step actually will be fatigue loading. Now, before we go on to the fatigue loading, let's tie up a couple of loose ends at here. Okay. This may not be actually a new topic. I think you probably learned already in the 260. So basically, it's a concept on stress concentration, and which leads us to a stress concentration factor. Okay, stress concentration factor. And I wanted to go over this concept again, and also, I'll at this stage, I'll introduce as actually in assignments, the bonus question in the next one, to use SolidWorks, to do a stress analysis. Okay, static stress analysis. And to compare notes with the stress concentration here, okay? Yeah. Okay, so what is the stress concentration? Okay. Let me bring this picture into my OneNote. Okay, so this is a bar with a hole in the middle, and this is another bar, okay, with discontinued geometries, and loaded, horizontally axial loading like this, right? Yeah. So if you cut a cross section at this non-uniform geometry location, okay, so that's a location with non-uniform geometry, right? Yeah. And then you look at the actual stress distribution at that cross section. Okay, yeah. So the observation you see is the stress. If it's just a regular cross section, then you should have basically a distribution, even a distributed normal stress, right? But with the non-uniform geometry distribution and like this kind of a location, the stress actually is not uniform. The normal stress, okay, it's not uniform. And the stress, if you see that in this case, okay, it becomes gradually increase and becomes maximum on this top and bottom location of the hole. So that's one observation. And same thing for this one here. If you cut a cross section, look at the shank area, and the stress distribution looks more like this, and you got a maximum stress at this location and this location. Okay, yeah. So this observation basically brings to the concept called stress concentration. Okay, stress concentration. Okay. There is the typical, basically sigma naught is called the nominal stress. Nominal stress. So what's nominal stress? Nominal stress is what we expect the stress to be. So in this case, it's probably, let's say, P over the area, right? That's your nominal stress. Right? And then we have, in this case here, we have a maximum stress. Okay. So the maximum stress, okay, so basically the location at the red dot location, okay, red dot location. So that will be a multiple, okay, or a certain scale proportional greater than 1, will be a greater value than this nominal stress sigma naught. So the KT at here is called stress concentration factor. For normal stress. Okay, so we have two different types of stress. One is normal stress, one is shear stress. Okay, so if you load it like this, you have the normal stress, and in this case you have the stress concentration factor, and that'll be for the normal stress. And if you have a bar and there's a discontinued cross section, something like this, we'll see it in one example. And if you twist it, then it's under shear stress, right? So we will have a similar situation, but then we use a KTS as a symbol, okay, in that particular case. So KTS we'll call the stress concentration factor for shear stress. Good. So basically, always bear in mind, whenever there's a discontinuity in the geometry for the parts, right? For the parts, then the location of this discontinuity will act as a so-called stress riser. So it tends to basically raise up the stress, right? And that's a very, very important thing to bear in mind, actually. So especially later, we'll also learn fatigue loading. This is stress concentration, and often in time is the location that will cause unexpected failure, okay, particularly under fatigue loading. So that's something that you have to always bear in mind. And this stress concentration factor is what we need to apply, okay, to reflect what the actual sigma max is. Okay. However, okay, I do need to make a very important comments at it here. Okay, very important comments. So this comment here particularly is for ductile material. Okay, for ductile material. So I want to jog your mind in terms of ductile material, right? So what's the nature of ductile material? Basically, if you apply stress, and initially it's proportional, right? Proportional strain change. And at somewhere, it reached this proportional limit. Okay? A little bit above this proportional limit, it'll reach the so-called what? Yielding point, right? Yeah. And then from this yielding point, depends on the material. Sometimes it probably have a drop, but sometimes it can. It will have a very small increase from the yielding location, right? And then you'll have probably another start to increase until it reaches this ultimate strength value and then breaks. Okay, yeah. Or even just until assuming the worst scenario, basically. You could consider this so-called plastic region. Maybe there's a certain region here. It's more or less like a flat, okay, flat region until the next stage. It starts to rise again and then break. Okay, yeah. So that's the nature of the ductile material, right? Yeah. Or it could be slightly increased, right? As I said, okay, slight increase like this. Okay, so either way is fine. Now, the nature of this one here is, if you think about it, right? If you think about it, especially from the ductile material point of view. So let's say if you have a stress, so you load it up, okay, and then you load it up to here, right? You load it up to here, and then you let loading go. If you want to let the loading go, because it's at this permanent deformation area. So once you let it go, it doesn't go back to, it's not like spring, it doesn't go back to the original length anymore, right? It'll retain certain deformation here. So it'll come back with a little bit permanent deformation here, okay? But what that means is actually, now the next time you load it, it'll load up to here now, right? It'll load up to here. So compared to the previous one, what increased? The yield strength increased. So that is called, if you recall in the review, is called the strain strengthening, right? That's called strain strengthening, basically. Okay? Yeah. So you have this, basically the so-called strain strengthening. Okay? The strain strengthening for ductile material. Okay? And if I give you, let's see, consider a situation like this. So let's say you have a bar like that case, and you load the bar on both sides with F. Okay? Yeah. And then we know that the critical maximum happens at here if you cut a cross section. Okay? Maybe it has a radius R at here, and then here has a the shaft side has a width of a D at here, and then it maybe have a width of T, right? If you look at the cross section, maybe you have a width of T at here. So your sigma naught will be equal to F over D times T. That's your nominal, right? That's your nominal at here. Okay, and then your sigma max, okay, is equal to, supposed to equal to KT times 0, right? Supposed to be equal to KT times 0. Okay, due to this fraction. So I'll show you how to find the KT based on this loading, based on this geometry. Your sigma max at this location, okay, supposed to be this. That makes sense? Okay. So now let's go back to this diagram in here. Go back to this diagram. You think about it. The sigma naught, let's say maybe, for example, sigma naught maybe is equal to 20 KSI, for example. Is that okay, right? Yeah. So I don't know what the KT, maybe KT equal to maybe 2, supposed to be 2. Okay? Yeah. But if you look at the actual ductile material, the property at here, okay? So what if the SYT value, so this SYT value here, what if the SYT actually is, let's say 33, okay, for example. Okay. So when you load up this shank area with this loading, and then supposed to be KT, what's the actual sigma max? The maximum is supposed to be about 2 times 20, which equal to 40, right? This is 40. But this ductile material, if you look at this one, you load up, it's supposed to be 40, but because the yielding strength is actually 33, so when you add this area here, the actual stress at that location is actually equal to what? Is it actually equal to 40? Equal to 40 KSI? At this location is actually equal to 33, right? Because that's the maximum existence of the stress at that location here. Is that okay? Right? That's the tricky part for ductile material here, right? So the KT theoretical value is 2. Theoretical value for stress rising is 40 KSI. But at this location, it's actually probably just a around 33 or 34, 35, right? So it's actually not going to reach that 40 KSI, okay? But of course, still, you know, when it reaches at this location, you do have a yielding, right? You do have a yielding here. So at this location here, okay, let's call this location A. So at location A, okay, so there is the so-called local yielding. Okay, there's so-called local yielding. And this local yielding will eventually give this strengthening effect. Okay, yeah. But if you look at not just the location A, if you actually look at this whole area here, right? If at this the whole cross section. Okay. What we see is there is no general yielding. Okay. So the stress concentration causes a local yielding at a location, and even at local yielding a location, the theoretical value of the stress is not the same as kT times sigma naught. Okay. And there's no general yielding. So the other, if you cut a cross section here, basically somewhere around in the middle or somewhere close to the edge, they are still okay. You know, they're probably still less than the yielding strength. So there's no yielding. So overall, there's no general yielding. There's only local yielding here, right? So that's the nature for ductile material. So what does that mean? So that basically means, this is what you actually have to remember now. For ductile material, under static loading, okay, there is no need to apply the stress concentration. Okay, there's no need to apply the stress concentration here. So if you're giving a static failure analysis question, and this part somehow contains a discontinuous geometry like this or like this, okay, then you got to be careful. If this is ductile material, don't apply stress concentration factor. Okay, just calculate the regular stress as it is, and then you apply apply the formulas for DE or MSS. Okay, then you calculate safety factor. But if it's a brittle material, then you need to calculate. You need to apply these two factors that are here. Okay, so basically, this is for ductile material. It's a no. Okay, and this is for static loading. There are a few things running in here. Ductile, static, no. And brittle, static, yes. Okay. Because next week, actually not next week, probably next week, yeah. When we learn the fatigue loading, so when we analyze the failure on the fatigue loading, it'll be different story now. There's still stress concentration factor, and then in that situation, we actually will apply the stress concentration for both ductile and brittle materials. Okay, so just bearing in mind of this. Okay, bearing in mind of this, and often in time when I give a question midterm, there might be a testing point, just trying to trick you whether you know this knowledge point or not. Okay, yeah, it's not a universal solution to apply this stress concentration factor to every kind of materials. Okay, so let's look at an example here. I'll through the example try to through an example to find the stress concentration factors using appropriate appendix in the textbook. Okay. All right. So the first example here, you have a part containing two different type of non-uniform geometry. Okay. So this is basically a hole at here, and then you have a fillet at here. Okay, a groove at here. Okay. So let's put a few labels, okay, for this geometry. Okay, consider there is a evenly distributed pressure force on the part. It has a cross section T, and these are the numbers. So D is 100 millimeter, and then the R is 15 millimeter. So let's the D. Forget this D. This D here. So that D is 50 millimeter, and T is 25 millimeter. Now, so let's call this is W here. Okay, let's call this W. Just want to differentiate from this D in here. Okay, so there are two different ones. We'll actually need to when we try to find the stress concentration factor, we're going to actually need to use a different basically appendix there. Okay, first let's look at the whole location. Okay, at this whole location here. So the whole location, first calculate the nominal stress. So if you cut a cross section at the whole location, right? Nominal stress basically is the force. Okay, this is Newton here. The force divided by the cross section area, right? The area of the cross section. So it's 45,000 Newton divided by the cross section area. So the cross section area is the capital D minus small d, and then times the thickness of the part. Plugging everything, so this is 1 millimeter, so this is Newton. So Newton divided by millimeter, you end up with megaparsec, right? So whenever you use a Newton here, then bottom here of millimeter, so you get a millimeter square. So Newton per millimeter square, the unit is megaparsec, right? Yeah. Okay, so then what is the stress concentration KT at here? Okay, so for this stress concentration KT at here, there's appendix A15 is what you need to use to find the stress concentration. And in this case, you where is that picture? A-15-1. A-15-1. Over here. So this is A-15-1 over here. Okay, let's paste it over here. Make it a little smaller. Okay, so this is the figure in A-15-1. Okay, that exactly conforms with the type of loading. You see this, you have a loading, axial loading, and you also have a hole at it here, right? Yeah. So given this figure at it here, this is how we can use this figure to find the stress concentration here. So from this figure relates to our dimension. In our dimension here, the small d over the capital D. Okay, so this W here is basically the capital D, the notation in our example here, right? So this one gives us a 0.5. So 0.5 is right here. So you go up, and then that's slightly above, below this 2.2, right? Slightly below this 2.2 here. Okay, yeah. So the KT in this case, this is 2.0, so this is a 2.1, so this is maybe 2.15. So you have to be, it doesn't have to be very accurate, but it has to, when you use a ruler, I think there's a certain range that has to be accurate, right? Yeah. So this one here will be approximately 2.18, I think, given accurate horizontal lines, okay, drawn there. Then your sigma max, okay, will be 2.18 times 36, which is 78.5 megapound. Okay. So that's how to use this figure to find the corresponding stress concentration factor. Okay? Yeah. So let's look at the other one there for this location, this notch location right here, right? So let's call this for the notch location. Calculating nominal factor, nominal stress. This is sigma n0. It's same P over. So for the notch here, right? It should be the whole D minus the top and the bottom, which is 2R, and then times the T, right? So minus the part removed, okay, and then times T. Okay. So that gives us 25.7 megapound. Okay. So then we need to find the KT. So for this one, you're going to use A-15-3. So I think we have this one here. Yeah, A-15-3 here. Okay. A-15-3, so let's see how we can use it, right? Horizontal axis is R over D, so it's the small r over the width, okay, between the two notches here. The vertical axis KT, and then you have a whole bunch of curves that's related to the ratio between your W over D, or in our case is capital D over D, right? So let's look at all of these things here. For our case, our capital D over D is capital D over D minus 2R, which is 1.43. And the small r over D in our case is small r over capital D minus 2R, 0.21. So once you have these two ratios, so now say 0.21, that's somewhere around here. So maybe it should be here, right? So you separate that into 5 sections. Then you go up until 1.43. So there's no 1.43. There is the 1, 2, 3. So that's basically somewhere between this 1.2 and 1.5. And then you can draw horizontal lines up to this location here. Okay? So that gives you approximately 2.0. So 1.9, 1.8, 1.9, and 2.0, 2.1, 2.2. Okay? Yeah. So your sigma max, right, is equal to 2.0 times 25.7, which is approximately 51.4. Okay. That's how you can calculate the maximum stress. In this case, it's a normal stress, right? It's a normal stress over here. Okay? Yeah. Yes.
Which appendix is that one?
Yeah, which, sorry?
Which appendix? Which table is that one?
Oh, this is appendix A-15-3. Yeah.
E? Okay.
Yeah, that's right. Yeah. Yeah, so there are different loading conditions, right? Then you actually need to use the right figure to find the right stress concentration factor. So you can. So this is a theoretical calculation, right? This is a theoretical calculation, and for this case here, you got a sigma max, which is this. So there's only this is if you take a stress element. So basically, all you have is the sigma max value. Because it says axial loading only, right? It's axial loading. And then when you have a axial loading only like this, if it's a ductile material, you can calculate sigma prime, which is basically sigma max. If it's if you want to use a brittle material, then you can calculate sigma A, sigma B. You'll get to what they are, right? Okay. Yeah. So you should try. You can look at how to use SolidWorks to do a stress analysis by giving the same basic dimensions, and then you can compare actually the theoretical calculation with the results from the stress simulation, right? So I have a video actually to deal with this one here, but this is very simple. So you basically fix one end, apply evenly distributed force on one end, on the other end, and then you can basically run a static analysis, and you'll get basically the stress values over there. So that value actually quite close to the theoretical value we calculated. Okay, yeah. And you can also run a simulation basically with a modified, stress element to become a little bit. The final elements is different, and then meshed differently, and then you get a different value, which is actually much more closer to the theoretical value. Okay. Another type of simulation you can do is you can do it on a part that is subjected to torque, okay, to torque only. So this is the part subject to torque, and then now you can try it. So there is a video in the lecture. There's a link. You can go over it by following the video there. So applying a torque at one end and fix at the other end, that's a typical, basically pure shear type of a test, right? And you have a discontinuity at here, so the maximum stress should be at this location at here. Okay, so given the nominal value, and then try to find the KTS. So KTS, you can look at the 8-15-8. For this loading condition, the KTS 1.3, then you find the maximum shear stress based on the theoretical value, right? Based on this loading condition, and you can calculate one mid-side stress, and then you can do a simulation. Okay, they are quite close to each other, so they're different. There's no way for them to be the same, but they are different. They're quite similar. So there's a link there you can follow. Okay, you can try to get the results, with the different physical scenarios, right? Yeah. So that's the point. Basically, up to this stage, this is everything about static failure for both ductile and brittle material. Okay. Yeah. Okay. So I'll leave that reading part to you. You can try it access. In the second assignment, which I'll post probably at the end of this week, there's an instruction how you can install SolidWorks. Okay. You will need that, I think, sooner or later for your projects. So you might want to do it now just to install it. Yes.
Why did you choose the max not the other value?
What do you mean, not the other value? Oh, I'm referring to this loading here. Yeah, this 78.5 is for this loading, right? Yeah. Okay. So we still have a few minutes here. I want to leave a question for you to exercise as a sort of a period of a summary or conclusion, right? So see if you have fully grasp some of the fundamental concepts yourself, and also give you a chance to test yourself how fast you can do the calculation. Okay. Okay. So here is one example right here. We have a solid round bar at here that is subjected to a loading condition as illustrated by the arrows. Okay, so the bar is subjected to three loadings: axial loading, bending moment, and a torque. Okay. The value of each one of them, the M equal to 55 Newton meter. The torque is 30 Newton meter. the pressure value, the force is 8,000 Newton. The material at here is what kind of material is it? Ductile material. So, okay, so ductile material as a YT is equal to 330 megapound. Okay. The bar has the diameter D, that is 20 millimeter. I think those are enough. Okay. Okay. So the question here is, okay, can you find the critical location and what will be the safety factor, okay, at that location? And n equal to what? Good. And I want you to be able to draw a simple stress element. Okay. So the stress element at that critical location. Draw it out, and then calculate the corresponding stress, or the numbers that needed for the formula for calculating the safety factor. So in my opinion, so this is basically, always the expectation, right? In my opinion, this is a very standard basically, not too difficult, not too easy, standard question, by applying what you learned to this kind of question, right? Maximum time you should take to solve this kind of question, 10 minutes. Okay? Yeah. At this stage, if you spend more than 10 minutes, it's fine, right? But when you're comfortable, then the maximum you should expect, especially in an exam situation, so 10 to 15 minutes. Okay. Okay? Yeah. Try it out yourself. See if you can get an answer within 10 minutes. Just exercise a few times, right? Yeah. I'll give you the answer next time. Okay, any questions? Okay, good.